Quick quiz. Two guitar strings have the same length and the same pull. One is thicker, the other thinner. Which sounds higher when you pluck them? A. The thicker string, B. The thinner one, or C. They sound the same. Lock in your answer. We'll come back to it soon. In this video, you learn how a string's thickness, its linear density, and how tight it's pulled, its tension, control wave speed and pitch. We'll model standing waves, work a few examples, and clear up a common misconception. Before we go deeper, remember, sound is a mechanical wave that needs matter to travel. No air, no sound. That's why a guitar in space would be silent. Light is different. It's an electromagnetic wave that can move through empty space on its own. The vibration on a string is a mechanical disturbance that travels through the string. Two properties control how fast that disturbance moves: the linear density mu, meaning mass per length, and the tension T, the pulling force at the ends. That wave speed follows a simple rule. V equals the square root of T over mu. That vibrating string then pushes on the air and produces the sound you hear. When ripples traveling in opposite directions overlap perfectly, they form a standing wave. The ends stay still. Those are the nodes. And the middle moves most. That's the antinode. For the lowest tone, called the fundamental, the frequency equals V over 2L, where L is the vibrating length of the string. So far, we've covered the core ideas. Wave speed depends on tension and how much mass the string has per unit length. The lowest note comes from that speed and the string's length. Thicker strings make lower pitches. Tighter strings make higher ones. Take a moment to lock in what you've learned before we return to our opening question. Want to check your progress? Tap the link for a quick practice test and a concise study guide tailored to this lesson. Quiz yourself, skim the highlights, and jump back in. Here's a common mix-up. Many people think thicker strings sound higher because they look tighter. In reality, thicker strings have more mass per length, which slows the wave and lowers the pitch. More tension does the opposite, speeding the wave and raising the pitch. Now, back to our quiz. Both strings have the same length and the same pull, but the thinner one has less mass per length. That lets waves travel faster along the thin string and gives it a higher fundamental frequency. So the correct answer is B. The thinner string sounds higher. Here's an example. A guitar string is 0.65 meters long, has a mass of 0.015 kilograms, and is stretched with a tension of 80 newtons. Let's find three things: its linear density mu, the wave speed V, and the fundamental frequency F sub 1. We'll start with the definitions and then plug in the numbers. First, the linear density mu equals mass over length, 0.015 divided by 0.65, which gives about 0.023 kilograms per meter. Next, the wave speed is the square root of T over mu, square root of 80 divided by 0.023, giving about 59 meters per second. Finally, the fundamental frequency F sub 1 equals V over 2L. 59 divided by twice 0.65, which is about 45 Hertz. Let's recap what we've learned. Thicker strings have more mass per length, so waves travel more slowly and the notes sound lower. Tighter strings increase tension, speeding up waves and raising pitch. Standing waves set the allowed notes, with still points at the ends and the biggest motion in between. That's how simple physics turns stretched strings into rich musical sound. Now that you've watched the video, let's see how much you remember. Head to the link in the description where you'll find Quizlet content made just for you.